and Venturi flume. Now, before we study about the flow measuring devices, so we solve this problem. So this is sample problem 10.8. Now, in the previous class, we studied about humps and contractions in open channels and how we analyze the open channel flow problems. Now, in this problem, we have uniform flow of water occurs at 135 CFS cubic foot per second in a 20 feet wide rectangular channel at a depth of 2 feet. So now the discharge is given, and the width of the channel and the depth of flow, these are given. Clear? Now this problem has several parts, so we will solve these parts one by one. The first part is that is the flow subcritical or it is supercritical. So let us first solve this problem, part A. So now we solve this part A of the problem. Now, since this is a rectangular channel, it is mentioned here that we have a rectangular channel. We can calculate the small q. So that is the discharge per unit width. So this is q is equal to the total discharge, which is given 135 divided by the width of the channel. What is the width of the channel? That is 20 feet. So we have this as 20 feet. This is actually what? This is actually the total discharge, and this is divided by the width of the channel. So we calculate the discharge per unit width, which is 6.75. 6.75. The units will be CFS. This is CFS per foot. This is CFS per foot. Now we can calculate the YC, which is the critical depth. So YC, this is equal to Q square is equal to Q square divided by G, and this power 1 by 3. Now you can put the values, take care of the units. Try to keep the units consistent when you solve the problem to avoid any possible mistakes. Now this answer comes out to be 1.123. 1.123 feet. Now the given depth, what is the given depth? Here this Y1, because we talk about the channel. So in the channel the depth is 2 feet. So it means that this depth, which is Y1, which is equal to 2 feet, it is greater than YC. It is greater than YC. What is YC? 1.123. So what it means, when the depth of flow is greater than the critical depth, so what we have, it means that we have subcritical flow. It means that we have subcritical flow. And the channel slope is mild slope, because when the channel slope is mild, we have subcritical flow. So this is answer to the first part, that is the flow subcritical or supercritical. So the answer is that the flow is subcritical. Why? Because the depth of flow in the channel, that is greater than the critical depth. Now you see here in this problem, we have this y1, and then the flow occurs over the hump, which is delta z. Over the delta z, because we have subcritical flow as we determined, so there is a drop in the water surface. You can see here, this is the water surface, but there is a drop, a depression. The water surface will depress down. This is because of this hump. So there is a decrease in the specific energy, which is accompanied by decrease in the water surface. And after the water passes from the hump, again the water will flow with the depth, which is y3. Now in this case, this is y0, the normal depth which is given in this channel, the normal depth here. Now in this case, we have this yc that we just calculated, this yc here, 1.123 feet. So there could be the possibilities here. You see that if we do not have this critical hump height, which will cause the critical depth to occur, so you can see that y1 and y3, they should be the same. They should be the level. Clear? Also, there is a possibility that when we have the critical hump height or greater than that, we see the z increases. Beyond that, then the y1 can increase. Means that the depth at the upstream side can increase. This is what we saw in the previous lecture. And we call this as the damming action. Similarly, there is a possible when we have the critical depth of the hump, then in that case, this critical depth of water will occur, and y2, that will be critical. That will remain as critical as you increase the hump height. Because we saw that when the height of the hump, it is equal to delta z critical or greater, still on the hump there will be the critical depth. Clear? So this y2, it has reduced to this, you see here, this y2, it has reduced to this critical depth, and it will continue to be critical. Now the y3 on this side, what will happen? Y3, which was equal to y1, it will reduce, because when the hump height is equal to the critical or greater than that, it will reduce. And this basically shows that this y3, it will become, you see, less than yc. So it will become the supercritical depth. As the delta z increases, it means that the depth immediately after the hump, that will be the supercritical depth. This is what you see in this diagram. So let us solve the different parts. We will see that these conditions that are shown here in the figure, these are fulfilled or not. Clear? Now in here you see the part B of the question is that if a hump of height delta z is equal to 0.30 feet is placed across the bottom of the channel, calculate the water depth on the hump and change in the water surface level at the hump. So now what is given in this part of the question is that we introduce a hump height. This is the delta z. This is now equal to 0.3 feet. This is now equal to 0.3 feet. And what we have to calculate the water depth at the hump. Means that this y2, this we have to calculate. Because now the depth will change because of this hump. So what is the value of this y2? This is what we have to calculate. And once we can calculate y2, then we can easily calculate the change in the water surface level at the hump. It means that what is this distance here? This was the water surface, and now this is the water surface. So now between these two, this here, this change in water surface, this we have to calculate. Clear? So now to solve this part B of the question, first we need to determine that this hump height is the critical one or not. So this we have to ensure first, because if this is the critical hump height or greater than that, then critical depth will occur. So y2 will be then the critical depth of flow. If not, then we simply can apply the energy equation to solve the problem. So what we do is that we can calculate E1. So E1 is equal to Y1 plus Q square divided by 2G into Y1 square. We can calculate the specific energy at point 1. This is the one here. This is section 1. And this Y1, this is given. So this will be equal to, this is 2 plus we have this Q. This is, we have calculated 6.75. This is whole square divided by 2 into 32.2. Take care of the system of units. 32.2 and Y1 square. So we have this 2 square. So now from here we can easily calculate this E1 is equal to 2.18 feet. Now if we have critical flow, so we can write down the energy equation. We will ignore the losses. This is given in the problem. So we write down the energy equation. So what is that? We write down E1, that is equal to delta Z critical. Actually we want to check that this point 3, is this less than the critical hump height or greater than the critical hump height? So accordingly then we can solve the problem. So we want to calculate this as the critical. So delta Z critical plus, if we have critical hump height, then the specific energy over the hump will be the minimum one. Clear? So that will be equal to E minimum. That is the minimum specific energy at the hump. This is E minimum 2 at the second point. Clear? Now this E minimum 2 we can easily calculate because we have the so this minimum E minimum, this will be equal to, we already calculated the critical depth. This will be equal to 3 by 2 YC. This is equal to 3 by 2 times YC, and YC we have already calculated. So you put the values. The critical depth was 1.123 as we calculated in part first of this problem. So this comes out to be 1.684. This is the minimum specific energy, 1.684 feet. Now from this equation here, so E1 we already calculated, that is 2.18 is equal to delta Z critical. This is the critical hump height plus we have this E minimum, which is 1.684. This is 1.684. So now we calculate delta Z critical from here. This is delta Z critical, and it is how much? 0.496. 0.496 feet. So now you can see that if the critical depth is going to occur, this Y2, if this has to be YC, then the height of this hump must be 0.496 or greater than this. So what is given? Actually we are given that this is 0.30 feet. This is given in the problem. So what we can say here is that this delta Z, which is given, how much it is given? This is equal to 0.30. 0.30 feet. It is less than delta Z critical. It is less than delta Z critical. Clear? Which is 0.496. So what it means? It means that critical depth does not occur. Critical depth will not occur. This critical depth YC, it will not occur. Clear? YC, it will not occur. Critical depth will not occur. So there will be no damming action. Now how to calculate Y2? Now it means that this concept we cannot apply, because the hump height which is given as 0.30 feet, it is less than the critical hump height, which is 0.496. It means YC will not occur, critical depth will not occur. So that's why this ensures that we now write down the energy equation. We again write down the energy equation between 1 and 2. And what is that? That E1, that is the specific energy at point 1, that will be equal to delta Z. Now no longer delta ZC. That will be equal to delta Z plus E2. Delta Z plus E2. Now E1 we have already calculated. So E1 is 2.18. It is written above, 2.18. Delta Z is given. It is how much? 0.30. And we have E2. So E2 will be equal to Y2 plus we have Q square divided by 2G into Y2 square. Now you see that the only unknown in this equation is Y2. Small q is known, G is known, and everything is known except Y2. So you have to solve this equation. You will get from here, you will get this equation that we have Y2 cube minus 1.877 Y2 square plus 0.707 equal to 0. So now solving this equation, it is a polynomial. Solving this equation, we will get 3 roots. So now we solve this equation, solving. So we will get 3 roots for Y2. One will be equal to 1.601, 1.601 feet. Second one will be equal to 0.817, 0.817 foot, and the third root will be negative. So that is equal to minus 0.541. So it will be equal to minus 0.541 1 foot. So now this negative root is not possible. 0.817 is also not possible. Clear? These two are not possible. One is physically not possible and these are not possible. The second one is not possible. Why? Because it is supercritical depth. So you can see, since the critical depth does not occur, what is the critical depth? The critical depth that we have calculated here, you see in here in the first part, we calculated the critical depth 1.123. Now when we solve this second part, this 0.817, it is not possible. Why not possible? Because the critical depth does not occur. So since the critical depth does not occur here at this point, that's why the water level cannot go to the supercritical. So that's why the answer is Y2 is equal to 1.601. This is the answer. This is the answer. 1.601 foot. This is the depth that will occur over this hump when we have this hump is 0.30 feet. This will be the depth that will occur. Now it is also asked that change in water surface level at the hump. So we have to calculate the change in water level at the hump. So what is that change? This is this change of surface which is shown here. You can see here this change of water surface we need to calculate. So change of water surface is now easy to calculate. You have all the data for that. So change of water surface that will be equal to what? That will be equal to 2. 2 is the depth here. This y1 is 2. So 2 then we have minus into this delta z, which is 0.3, that is given 0.3, and we have calculated y2. So how much is y2? 0.3 plus 1.601. 1.601. So 2 minus into this summation. So this will be the change in the water surface. How much? This will be equal to 0.099 feet. 0.099 feet. This is the change of the water surface. So this is part B of the question. Clear? Now next we go to part C of the question. So in part C of the question, it says that if the hump height that is raised to delta z is equal to 0.60 feet, what then are the water depths immediately upstream and downstream of the hump? So now in part C, delta z is 0.6. So in here, this delta z, which is given 0.6. So we already calculated the critical hump height. This is equal to 0.6 feet. So this is already greater than the critical hump height as we calculated in the previous case. What is the critical hump height? Delta z critical, that is equal to how much? 0.49, 0.495 or 6. Clear? So it means that critical depth will occur. Critical depth will occur here. This YC, this will become YC here. This critical depth will occur, which is given in the figure as Y2. So this Y2 will become YC. Why? Because now this delta Z, this is greater than the critical hump height. So critical depth will occur. So How to solve it? Now it's easy. This will be equal to E1, which is the specific energy at section 1. And now we write down also the energy here. E1, that will be equal to delta Z. That will be equal to delta Z plus E minimum. Because if this delta Z is critical or greater than the critical hump height, still the critical depth will occur. Clear? This is what we already discussed in detail in the previous lecture. So we have delta Z and plus we have E minimum, the minimum specific energy. We have the minimum specific energy at the second section. So now in this case, we want to calculate what? Because the hump is greater than the critical hump height. So there will be damming action. Clear? There will be damming action. So it means that the depth will no longer be 2 feet here. The normal depth which is given here in the problem is 2 feet. But now that the hump height, it is greater than the critical hump height. So that's why as a result of that, what will happen is that there will be a damming action. So the water surface, it will be like this and it will reduce to the critical. So you can see here that now Y is different. This is now Y1 that we have to calculate. This is due to the damming action. This effect here, this is known as the damming action, as we discussed. When the height of the hump, it is greater than the critical hump height, so what will happen is that it will result into damming action. The height of the water on the upstream, that will increase. Clear? So that's why we have E1 and Y1 is unknown. So this E1 will be then equal to E minimum. We can already calculate, and this will be equal to Y1, which is now unknown, plus we have Q square. Discharge is the same. Discharge is not going to change. So Q square divided by 2G into Y2 square. And this will be equal to delta Z. What is delta Z now? It is given 0.60 feet. So this will be equal to 0.60 and plus we have E minimum. So E minimum we already calculated. Clear? This will be equal to 3 by 2 YC or 1.5. 3 by 2 YC and YC is 1.123. 1.123. Clear? Now in this case, the only unknown here is Y2. So the only unknown is Y2. So you have to solve this for Y2. Now solving this equation. So when you solve this equation here, we will get again, because it is a polynomial, so we will get, this is Y1. Actually not Y2, sorry about this. This is Y1. This is Y1 and this is Y1. We are talking about the upstream depth here. So this is Y1 and you will get the values of Y1. Why Y1 has changed from 2 feet? Because of the damming action. Because this delta Z is greater than the critical hump height, so there will be damming action. And because of the damming action, the depth upstream, that will increase. So that's why Y1 is unknown. That we have to calculate. So now this will be equal to 2.13 feet. This is one solution to the above equation when you solve, or this can be equal to 0.66. This can be equal to 0.660 feet, and the third one will be negative, that is minus 0.5 0.504 feet. So now negative depth is not possible. So since damming action occurs, since we have damming action, so the water depth will increase because of the damming action. So that's why y1 will be equal to 2.13 feet. So this is the answer. Y1 is equal to 2.13 feet. Clear? Now, in the question, it says that what are the water depths immediately upstream and downstream of the hump? So this is the upstream. Clear? This is the upstream. So the upstream depth, that is Y1, that is Y1 is equal to 2.13. Now, what will be the downstream depth here? It says that when it passes through the critical depth here, so what will be this depth here? Immediately downstream of this. Now, immediately downstream, what will happen is that the depth downstream of the hump, it must be the supercritical depth. The depth downstream from the hump cannot be the subcritical depth. This 2.13, it cannot be here. The reason is that because of this damming action, it gains the energy that is to flow over this hump. Clear? So this energy, extra energy, it has to dissipate. And this dissipation has to be some mechanism where it needs to dissipate the extra energy and return to the normal depth. So if immediately after this hump we have subcritical depth, this 2.13, then it will not dissipate the extra energy. So that's why this is not possible, and we say that depth downstream, this is after this depth immediately downstream is how much? It will be this 0.66. This is the supercritical. This is the supercritical. Clear? So that is immediately downstream, that is 0.66 feet. This effect I will show you when we discuss the broad crusted wear, that why it should be a supercritical depth. It should not, cannot be 2.13. What here we are assuming is that we have this channel and then we have this hump which is greater than the critical hump height, as we are solving in the problem here, greater than the critical hump height. So due to the damming action, the water surface has increased. It will come down to the critical depth here, and then it will further decrease to the supercritical depth, and then there will be a hydraulic jump to dissipate the energy, and then the water will flow with the normal depth in the channel. This is the situation. This I will show you in the broad crusted wear also. You will see this later on in the picture. So it has to dissipate the energy, and that energy has to be dissipated by the hydraulic jump. What we want to say is that this is not possible. You see, if we have this hump height and the water comes with the damming action, and then it comes to YC, and then after YC again it come here, this is not possible because this depth is due to the damming action. It's not possible. Clear? So a damming action, it has gained the energy here, because you see here Y1 is no longer 2. What is actually Y2? If I go back to the problem statement, actually it says that the depth is 2 feet. In the channel, the water flows with 2 feet. But now we have damming action. Clear? Now we have damming action. So because of the damming action, the depth has increased. So it means that it has gained the energy. It has gained that extra energy to flow over this hump at the critical depth, and in order to return to the normal depth, it has to dissipate that extra energy. So that is only possible if the depth downstream of the hump is supercritical depth. So immediately after this, there will be supercritical depth here, and then it will dissipate the energy by the hydraulic jump. This we will study in detail later on. This is the rapid wear relief phenomena, and this I will show you in today's lecture when we study the broad crusted wear. Let me go back quickly if I can see the broad crusted wear to just show you what I'm saying here right now. Here you can see here we have this normal depth. In this case we have this normal depth, then the depth reduces to the critical depth here, and this is due to the damming action for this here, you see, due to the damming action, and immediately downstream you see the depth is less than, this is the subcritical depth. You can see here the subcritical depth immediately downstream, and then this is the hydraulic jump. So it will dissipate the energy here, and then after that you can see that from this immediately lower depth, again it has to go to the normal depth and continue, the water will continue to flow in the channel. So that's why what we say here is that in this case it has to, the depth has to be 0.66 feet. This is the depth downstream. This is what asks that what are the water depths immediately upstream and downstream of the hump. So the immediately downstream, the depth must be the supercritical depth, and then there will be dissipation of the energy, and after that it will become the normal depth and the water will flow in the channel. Clear? So this is part C of the question. Now part D of the question is that if the 0.30 foot hump is accompanied, it is combined by a local contraction. Now we are combining the two effects, that this 0.30 foot hump, it is accompanied by a local contraction. It means that the channel width is also reduced to 18 feet. What is the channel width actually? 20 feet. Now it is reduced to 18 feet. So find the water depth on the hump. Now what is the depth here? Again we have to calculate this Y2. So this Y2, this is now unknown. This Y2 is unknown. And now we are combining the hump and the contraction. So because of the contraction, so what is happening is that you see in the problem, what is given is that the channel width is 20 foot. And now it is reduced to 18 feet. So it means that the channel is 20 feet and now it is reduced to 18 feet at the hump. The channel width is reduced. This is, and it is combined with this hump also. At this point we have hump also. So it means that this width of the channel, that is 20 feet. That is 20 feet. And here the channel at the hump, that is reduced to 18 feet. So now what we are doing at the hump, we have now delta Z and also there is a contraction. So we are now combining the two. So now the question is that because of this, what is the depth of flow? What is the depth here? What is this Y2? Clear? So neglect the losses. This is what we have done in all the cases. So now in this case, first we see that this section 2 now, we talk about this 1 and this is section 2 now here. So first we need to see is critical hump, this critical depth will occur or not because of this hump which is 0.3 feet and also there is a contraction to 18 feet, the width of the channel. So will critical depth occur or not? So for that we need to calculate what is the critical hump height. Now because the width of the channel that is reduced, so at section 2 what will happen? The discharge per unit width that will increase. The total discharge is the same, the total discharge is not going to change, but the discharge per unit width that is increase. So what we have is that at section 2 at section 2, what we have is that this small q, that will be equal to the total discharge, which is 135. That is not going to change. Now the width has changed from 20 to 18. So discharge per unit width will increase. This will increase. So this is how much now? 7.5. Discharge per unit width has increased. This is 7.5 CFS per foot. Discharge per unit width. Now for this we can calculate YC, because YC will change. It depends on the discharge. So this YC at section 2 will be then equal to this small q. So this will be equal to q square divided by g into power 1 by 3. So this is equal to 1.204. 1.204 feet. Now we calculate the minimum specific energy. So the minimum specific energy at section 2, that is equal to 3 by 2 times YC, as we already proved these for rectangular channel. This is a rectangular channel. 3 by 2 YC. YC is 1.204. So this comes out to be 1.807. This is 1.807 feet. Now we calculate delta Z critical. So this will be equal to E1 at section 1, the specific energy, that will be equal to delta Z critical plus we have this E minimum at the second section. Now delta Z critical is how much from here? Delta Z critical, so this will be equal to E1 minus, this is E1 minus E minimum at the section 2. So you put the values. So we get this as equal to 0.373. This is equal to 0.373 feet. Now you can see what is the given hump height, that is 0.3 feet. And if we want to have a critical depth here at the second section, then the hump height should be 0.373 or greater than that. Clear? So since the delta Z, which is given 0.3 feet, it is less than the critical hump height, delta Z critical, which is 0.373. So critical depth will not occur. Clear? 0.373 feet, it means critical depth will not occur. So therefore the combination of hump and contraction will not cause critical depth or damming action. Clear? So when we combine the hump and contraction for this given case, critical depth will not occur, means there will be no damming action. So what we do is that E2, the specific energy at section 2, that will be equal to E1, the specific energy at section 1, minus delta Z, which is 0.3. So you just need to put the values here. So this E1 we already calculated here. What is E1? Did we calculate this E1 here? 2.18. This E1 here we already calculated 2.18. So this will be equal to 2.18, and delta Z is given, which is 0.3. This will be equal to 1.88. So now in this case, we have 1.88. This is your E2. Clear? So this will be equal to 1.88, and E2 is also equal to Y2 plus Q square divided by 2G into Y2 square. So now everything is known except Y2. So solving for Y2, so we will get this Y2 that will be equal to 1.48. This is the answer. When we combine the hump and the contraction, so the depth of water over this hump, that will be equal to 1.48. Now to summarize what we have done, so you see that this Y1, it was given as 2 feet. Then in this case we come here, so this 2 feet, we proceed along this line here, and this is the specific energy curve, this one here, for Q1 is equal to 6.75. Now from here in the part B of this question, the hump that was provided with 0.30. So because it reduced the specific energy, so you see that from E1 with 0.3 we come here. So we come here this E2, and then from this E2 we proceeded, because critical depth did not occur, we proceeded here, and this was the answer. This was the answer, 1.601. This is what we calculated, that the depth Y2 is 1.601. Clear? And for that you can also calculate YC. Here you can calculate YC. Then what happened in part D of the question, this is part D of the question, the hump, this 0.3 feet hump, it was combined with a contraction. So with this contraction, the discharge change. So now the discharge change from 6.75 to 7.5 CFS per foot. The unit discharge change. The total discharge is the same. The discharge per unit width increase because the width is reduced. So now for the same E1 and E2, you see that instead of here, then we come here, since critical depth does not occur. So now we come here for this second energy curve, and we reduce here to calculate this Y2. And what is this Y2 here? 1.48 feet. This is 1.48 feet. This is the answer here, this one here, 1.48. So this is how we calculated. Clear? And because the unit discharge, it changed, discharge per unit with change, so that's why you can see that we have the another value of YC, because YC is dependent on the discharge. So the discharge per unit width increase, so that's why YC from here, YC increased to here. So this is how we solve the problems. So with this, now we start the next topic, that is control of flow. We discuss now about the flow measurement devices. So there are many devices to measure discharge in open channel, but as per our syllabus, we will focus on two important devices. So before we discuss them, we have the control of flow in an open channel is defined as a definitive relationship between the stage means the depth of flow, and the discharge of the flow. So as you saw that when we have control of flow, if you remember, we discussed the occurrence of critical depth, and we stated that that is the control section. So when we have this specific energy diagram, so at this point here, when we have the minimum specific energy, when we have the minimum specific energy, so for that we have one possible depth, that is YC, and it provides a definite relationship because for other specific energy there are two possible depths which can occur for the same discharge and same specific energy. But there is only one depth corresponding to the minimum specific energy, that is the critical depth. So that's why we are interested for occurrence of this critical depth, because it provides a definitive relationship between the stage, means the depth of flow, and the discharge. So remember this stage word, you will study hydrology in the next semester, so you will see the stage discharge relationship. So actually when we have this channel, so normally what we do is that the depth of water with respect to this bottom, so this is normally we call it as the depth of flow. But when it is with respect to any other datum, for example, this you consider as the datum, this we call it as the stage. Clear? So this Y is also a stage. But this is generally with respect to any other datum that you can consider, that is called the stage. So that's why it is written between the stage and the discharge of the flow. So the control of flow means in an open channel is defined as a definitive relationship between the stage and discharge of flow. When the control of flow is achieved at a certain section of the channel, this section is known as control section. Clear? We already discussed this. The flow condition in a subcritical channel is affected by downstream conditions, but in the supercritical channel, the flow condition is dependent entirely upon the condition upstream or at the place where the water enters the channel. So what we can say is that the control of flow, that is said to be the downstream end for channels and with subcritical slope at the upstream end for channels with supercritical slope. What it means? It means that when we have the subcritical flow in a channel, you will see that the control of flow will be at the downstream end. And when we have a supercritical flow slope, then the control of flow, it will be at the upstream. This we already discussed in the previous lecture. Let me give you back to that topic that we discussed, the occurrence of critical depth. So if you remember, we have this subcritical flow in a channel, and this section here, this is known as control section. This is known as control section. So you can see that this control section is at the downstream end. This is the downstream end of the subcritical flow, because after this you have supercritical flow. So that's why it says here that the control of flow is said to be at the downstream end for channel with subcritical slope and upstream end for channels with supercritical slope. For example, we also discussed this thing here. When a water enters from a reservoir to a canal, so you can see here the depth in this canal is less than YC, so it is supercritical. But in here you see that at this point it passes through the critical depth, so that's why this is known as control section. This is known as control section. This we discussed in the previous class. So you see here, that's why it is written that the control of flow is said to be at the downstream end for the channels with subcritical slope and at the upstream end for channel with supercritical slope. So this is what you can see. This is now the flow in the channel is supercritical, but at the upstream end you have control of section. But when we have subcritical flow, at the downstream end we have control section. Even in the broad crusted weir also, that is what we are going to study in detail right now. You will see that when we have a broad crusted weir, I show you the picture also, we have this subcritical flow. Then we have the critical depth that has to occur over here, and then the water can flow. There will be hydraulic jump, and then the water can flow with normal depth. So you can see here for subcritical situation, here you see that at the downstream we have the control flow. Here the YC has to occur. This is for the broad crusted weir. We are going to discuss this in detail. So these are a few points need to understand for clearing the concept. Now we discuss the flow measurement in open channels. Remember that we have different devices that can be used to measure the discharge in open channel, but as per your syllabus, we will only focus on two devices. Clear? So what are those two devices that we are going to study in this topic, flow measurement in open channels? Clear? So at the critical state of flow, a definitive stage discharge relationship can be established. As I already said, therefore, a critical flow section is a control section. Such a definitive stage discharge relationship offers a theoretical basis for measurement of discharge in open channels. As we already discussed the basic equations, clear? So such a relationship between the depth of flow and the discharge, that relationship that offers a theoretical basis for the measurement of discharge in open channels. So based on the principle of critical flow, various devices for the flow measurement have been developed. So there are many devices. We will primarily focus on two devices as per our syllabus. So in such devices, the critical depth is created by the construction of a low hump on the channel bottom, such as a weir, or by a contraction in the cross section, such as a critical flow flume, which was also known as the Venturi flume. So now under this topic, flow measurement in open channel, we will primarily focus on two devices. One is the broad crusted weir, and the second one is the critical flow flume, also known as the Venturi flume. So now just I will briefly refresh your memory about the weirs first, a very brief introduction and discussion. I will not go into detail because weir notches you have already studied in your Fluid Mechanics 1 course. So I will be just very brief on these weirs and notches, what you have studied, and then my main focus will be on the broad crusted weir and Venturi flume. So let me just quickly and very briefly discuss the weirs. So we already know that a weir is a simple overflow structure extending across a channel and normal to the direction of the flow. So weirs can be used to measure the discharge rate in an open channel. We are using weirs notches. So these are used for measurement of discharge. They can also be used in water management to control the discharge rate from reservoirs and detention basins. So basically these type of structures, these are provided to control the discharge rate from reservoir and detention basin. You can see, for example, in this case, there is a pond as a result of this structure that we provide. So not only you measure the discharge in the channel, but also it is used in water management. This you will study more in detail in another course known as irrigation engineering. Clear? So they are also used in water management to control the discharge rate from reservoirs and detention basins. Those basins, they detain the water. Clear? So primarily what we are discussing them here is for discharge measurement purposes. And then there are different types. You can see here, this is a rectangular one. This can be a rectangular one. This is a triangular one. This is a triangular one. And also a trapezoidal shape, different shapes that you already discussed in detail in your Fluid Mechanics 1 course. Let me just very briefly go through these things. So first we discuss the suppressed rectangular weir. I will explain what we mean by suppressed weir. So now in this case, we have this open channel, and then we have this weir, which is a raised structure, and this is the top of the weir. This is known as the crust, sill or crust. And what will happen is that the water will flow over the crust. Clear? This is the crust, a rectangular weir. So the water will flow, and this sheet of water which flows over the crust of the weir, that is known as nappe. This is known as nappe or veen. This is the sheet of liquid that is flowing over this notch or weir. Clear? So P is the height of the weir and H is the head of water. And because this water is approaching the weir with a velocity that is denoted by V naught, this is known as approach velocity. This V naught is known as approach velocity because this is the velocity with which the water approaches the weir before it flows over the weir or notch. This is known as the approach velocity. It is denoted by V naught. And you might have discussed in Fluid Mechanics 1 how we can determine this velocity of approach. So this is known as the velocity of approach. The velocity with which the water approaches the weir or notch before it flows over it, that is known as the approach velocity. So that's why it is shown here, V naught square by 2G. Now, you already developed the formula for this, how to calculate the discharge. So you already discussed the formula here, that for a rectangular weir, I will explain what we mean by suppressed. So Q is equal to CD, which is the coefficient of discharge, that is equal to 2 by 3. You already did practicals also in your Fluid Mechanics 2 lab. So this is equal to under root 2G into L, which L is the length of the weir. Clear? This is the length of the weir. And into H3 by 2 into H3 by 2. Okay, so this is the basic equation. Q is equal to CD 2/3 of into square root of 2G into L H3 by 2. This is the formula for rectangular notch or weir. Clear? Now in this case, this CD, this is actually the coefficient of discharge. So this CD for sharp crusted weir, you see here, this is sharp. The sill or crust of the weir, you see here, this is sharp. So that's why this we call it as sharp crusted weirs. So we call them as sharp crusted . This is known as sharp crusted weir. So now for this sharp crusted weir, so with flowing range of about, you see, when we have, for example, this is 0.62, this CD, we talk about this CD. This is CD, the coefficient of discharge. You already know how we can calculate this experimentally. So this is 0.62 for H by P. This is the ratio H by P. This is H and this is P. This H by P equal to 0.1. And this CD, this is equal to 0.75 for H by P, that is equal to 2. This is written in your textbook, not in the open channel chapter, but in the flow measurement, chapter 11. You can see the article 11.11. So that is related to this weirs, notches and weirs. Clear? Chapter 11 of the textbook. You can find these equations there. Clear? Now, for this rectangular where this CD you have to estimate very accurately. This CD is equal to 0.605. This is equal to 0.605 here, plus 1 divided by 305 times h, 305 times h, plus 0.08 into h by p. This h by p here that we talk about, this is equal to h by p. So these expressions, these were developed, these are empirical. So these were developed by conducting experiments. This is equal to 0.605 plus, this is in BG units. The first one is in British gravitational system. This is in BG units. And this is in SI units. So that CD will be equal to 0.605 into 1 divided by 1000 H plus 0.08 H by P. So now these equations were developed by conducting experiments. Clear? We can calculate this CD needs to be calculated as accurately as possible. If you want to accurately measure the discharge, you already conducted the experiment how to estimate the value of this CD. Clear? Now you can see here that the discharge, when we write down the discharge, so it is actually a function of this W into R, which is the Reynolds number, and equal to H by P. This is equal to H by P. W is the Weber number into L into under root G into H3 by 2 into H3 by 2. Now in this case, you see that CD depends upon WR and HP. This here that we have written here, this is for CD, that CD depends on this WR and HP. And this H by P, it has been found that this is the most important. This W here is CD depends on these things. So let me finish this. Now it has been found this W, that is the Weber number. This W that is actually equal to the Weber number. This is the Weber number. We will study dimensionless number after the midterm. So this Weber number actually is the, it accounts for the surface tension. This accounts for the surface tension. Accounts for surface tension. Clear? So now capillarity is accounted for by this second term. In this case, you see in this equation, this second term here or here, this is this accounts for the capillarity, clear? While the velocity of approach, which is assumed to be uniform, that is responsible for this last term. These last term, these are velocity of approach. These are responsible for this last term, clear? So instead what we do is that this equation, these are available in your textbook chapter 11. This we write down as Q is equal to CW into L, where CW is the wear coefficient, clear, into H3 by 2 into H3 by 2. Let's say this is equation number B. So this CW is the wear coefficient. This is the wear coefficient, clear? Actually what is happening that this CW, it replaces that CD 2 by 3 under root this actually replaces CD 2 by 3 into square root of 2G, coefficient of wear. So it is written in this equation B form. You will see in your textbook chapter 11, you will see this form of the equation. So the idea here is that we can write down very easily this equation, that this is equal to 3.32 times L H3 by 2, and this is equal to Q is equal to 1.83 times L H3 by 2. So this equation, that is in the British gravitational systems, in the BG units, and this equation, this is in the SI units. So you have all studied this in your fluid mechanics 1 course. I am remembering just very brief and just to refresh your memory about this before I come back to discuss the broad crusted wear, clear? So let us take a break, then we will continue after the break.